So we are open for questions. Okay, Frank, are you also applauding or are you asking a question?
Both. So thank you very much, David, for this nice talk. Maybe I can switch on my camera. Yes, concerning at some point you showed some spectra. Could you show them again? In the strong field solution there.
I think that was the one with the typo. Yes.
Yes. Because you didn't split between between the two types of U. You could have done that.
No, I could. That's right. You mean for the spectra?
Yes.
Yeah, that would have been an interesting thing to do in a way. I mean, we know now what it must look like actually, but that would have that's a good point. I mean, because we've from that decomposition in the thermal equation, we know that the viscous terms don't matter. So if I did it for the thermal equation, it would really kind of come down. You know, it would have large scale, and that would be that. Whereas for the other one, well, it would certainly have small scales. I'm not sure. Yeah, that's an interesting point actually, Frank, as to how much of the large scale could be split. Yeah. If it were true Taylor, if it were a true Taylor state, this thing would come along and just finish. You know, there would be nothing over here. But yes, I could have done that. That would have been an interesting thing. Yeah. Good point.
Okay. Thank you. Thank you. And maybe another question. So from the beginning, you mentioned that you neglect the inertia terms, but in fact you have two terms, time derivative and U grad U terms. If I remember well, usually the people neglect the U grad U term but keep the du over dt. Some people do that.
Yeah, they do.
And what's the difference?
Well, it's not clear why you should do that. Because you might think that the dtu and the u dot grad u are comparable. My feeling is that's an easy way. Well, it's an easy way of doing it in some sense. It depends. I mean, this might not be fair, but you might say that I don't want u dot grad u because I want to be a low Rossby number, but I don't want to change my code dramatically.
Oh.
Because if you get rid of dtu, you have to change your code dramatically because you have to invert for the velocity at each time step. So if you've got a time stepping code, it's very easy, of course, just to lob out a u dot grad u term, which they won't bother with it. And off you go. And if you do throw away the dtu, you've got to do a lot of code modification because you've got to invert for the velocity. And okay, so there's a lot more, you know. That's what we did. And we kept getting it wrong, so I can see, and we're in plane geometry where these operators are quite well behaved, if you like. It's much more, to do all that in spherical geometry, for example, is more messy for sure, and so that's one reason why you might not do it. But you might then end up chasing high frequency inertia type waves that you don't want. But people do that, and I think that's why they do it. Possibly that's mistaken, but I can see that's a good reason to do it.
Okay, thank you.
Can I comment on this the same question?
Yeah,
I believe it is on Frank. It is quasi-static approximation. The time scales. So in MHD, quasi-static MHD. So if the magnetic field is too large, then the u dot grad b, the nonlinear term, is dropped because the time scales are too different, and d by dt basically we should not try to follow the small time scales. So I can send you some more stuff on that. But is the time scale is a quasi-static approximation? I think that's when we can just ignore the d by dt as well. So I'll send you some reference on that.
Okay.
Both of you. Okay. Yeah. So the next question is by Abhishek. Abhishek, go on.
Yeah. Hi, David. Thanks for a very nice talk. So I was thinking about the force balance in this thermokinematic problem. So in that case, the U dot grad T, that would probably have a significant contribution, isn't it? And you chose not to show that. I was wondering why that is the case.
Oh yeah, I'm only. That's right. I'm only balancing. So I'm only showing the force balance in the momentum equation. Yeah.
Okay, so it's not the temperature equation that was used for the thermokinematic problem.
So we do. Yeah, sorry, I probably wasn't clear enough. So we have. So the problem in the thermokinematic problem is
Okay, it's not this equation.
No, so this is the equation we solve for the temperature.
Right. Okay.
So what we had in mind was the full convection problem. Of course, is kind of sneaky because you can change the velocity through the induction equation, through the field, and then that changes the temperature through the temperature equation, and that drives into the thermal velocity. So you can get large scales in the thermal velocity, which of course is what happens. That's the crux of it. But as a comparison problem, you might say, well, suppose what we thought at first was we could just force the problem. You could put suppose you did, I don't know, helical forcing or something, just put, which would be quite interesting. You just put the forcing in with the Lorentz force. Then that's a sort of simpler problem because the force is just there doing its stuff all the time. It's different to convection. And we thought, well, could we do an artificial forced convection problem? We thought, well, yeah, we can. We can just force small scale convection. And how we force small scale convection is by keeping this as a distinct velocity from U. It's not U. Mm-hmm. So we have a small scale thermal convection driven all the time. But in the things I was showing you, they are all from the momentum equation.
Okay, so the difference of that compared to the full problem was the UT.
Yes.
The UT, the temperature equation, is the difference.
That's right. So that's right. In the thermokinematics problem, it's what we call UT.
Okay.
Whereas in the real problem, of course, it's U, which is UT plus UM. So we're not, in the thermokinematic problem, we're not allowing the temperature to go to large scale. That's the difference.
So is there a way to evaluate whether this approximation of U as UT, is that a good approximation? For example, by adding up all the force terms and finding out if the sum is 0. So let's say if we bring all the force terms on one side and compute them, and if they turn out to be 0, then I guess this U as UT was a good approximation. Maybe this is just one way. There could be other ways also.
Yes, I mean that's right. I mean, but that yes, and that's sort of what happens in the weak field dynamos. So in the weak field dynamos, there isn't really much difference between the full problem and the thermokinematic problem.
Right. Yes.
Because the velocity is essentially, of course, it's changed a little bit, but it's on that scale. And so if you really went to a really weak field dynamo, there would be no difference between the two problems, and the difference becomes larger the more you go into this strong field regime, because in the true strong field regime, you're allowing large scale thermal velocities. That's crucial, really. But in the kinematic problem, thermokinematic problem, you're discounting them by construct,
Right. So I'm curious to know something more about this VM-Mach balance. So in the spherical dynamos, for example, the Yadav and Schaefer's, their papers, the viscous force contribution is several orders of magnitude smaller, and one could project that if we go to much smaller Ekman numbers, that would become even more smaller. So in that case, is there a signature of this magnetic viscous force contribution, if I can use that word? I haven't come across any result in the spherical dynamos where we could, think about this type of VM Mac balance.
Yeah, I mean, it only makes sense in a true in this decomposition that we have, right?
But if it is significant, then would it it should show up in some of the full spherical simulations as well. And if not, then is this really important?
Well, my own feeling is that it's not clear from the diagnostics that Schaefer and company do that the viscous term is not important.
Mm-hmm.
So, but of course they've got E del squared U, so they can't really talk about
right
E del squared UM like we can.
Right.
But you see what I mean? It's a different geometry, and they tend to do averages. I mean, what they find, as you know, is that that they're not spatially inhomogeneous. Of course, sort of their inner bit and their outer bits are very different.
Right.
And then they sometimes do averages over the inner bit, and so it's almost as if they've got Mach balance in parts of their domain and not Mach balance in the rest of the domain. That's not something we would have in this planar geometry. That's to me how it looks for them.
So is would the boundary conditions play any role, because you have not used no slip?
Can I interrupt? Let's go to the next question and we can come back. Okay.
Yeah, sure. Yeah.
We can leave discussion because the two people are waiting, so we can extend the discussion. Huh?
Yeah, right.
Sorry. I just want to interrupt with the moderator. Okay, Savik, please go ahead with your question. Savik.
Yeah. Hello, David.
Hi.
Thanks for the talk. So I am also studying the same problem in my PhD, but my focus is on the heat transfer of the system. And I'm solving for the full equation, but with no slip conditions in the top and bottom plate. So how do you think the role of the viscous force may change if we consider these Ekman layers near the top and bottom plates and using no slip conditions?
Yeah. That's why we didn't use them. Well, it will change, and I suppose you might have sort of Ekman pumping and things like that. I mean, I think that's only going to make it worse in some sense, in that. So we were, I mean, all our viscous terms are not, of course, they're not due to Ekman layers. They're due to internal structures. And it seems to me that you're still going to get those internal structures.
So the force balance I'm referring to is a volume average balance, of course. And I'm talking about very small Ekman numbers. So I'm using 10 to the power -7.
Okay.
The Ekman layers are very thin. So do you think in a volume aberrations, if I calculate the force balance, it will be very different from the stress-free conditions values?
Well, I mean, I can see, okay. I mean, I can see that it's probably not so easy to get. So in my thermal velocity, I had this great offset of Coriolis and buoyancy term, and the viscous term really was insignificant in that. Now that might not be true. I can see that could see that might not be so readily satisfied in no slip. Yeah.
Okay.
But in terms of the fundamental problem that that I was trying to highlight in a way, which is the magnetic viscous terms, I don't think those will go away with, I mean, I think there'll be complications because of boundary terms, but I think all the internal dynamics will still give you that issue.
Thank you, David.
David, maybe I just make a comment on Sauvik's question. So yes, we did quite a bit of convection simulation, pure thermal convection, with the no slip and free slip. And that experience, I could say something. So it turns out that boundary layer, of course, has a very important physics, but the bulk dynamics, spectrum, for example, and the force balance between pressure gradient, nonlinear term, all that in the bulk remains the same for both free slip and no slip. So if your magnetic field generation is dominated by bulk motion in the box, then the results I expect for no slip and free slip to be roughly same. That is my guess. Okay, I hope. I don't know. That's so it works for thermal convection. We find the bulk plays a major role in Nusselt number, for example. It is more, but it's roughly of the same order.
Okay.
You understand?
Thank you. Thank you.
Boundary layer doesn't really. I mean, force balance works for boundary layer. Okay. Anyone else has a question? Okay. So
yes,
David,
Mahendra, can I ask a last question?
Please.
You didn't mention the magnetic Prandtl number value in your talk.
Well, yeah, because it's which way round is it? It's infinite.
It is infinite, huh? Yeah, this is.
Yeah, okay. Because it's the Roberts number times the.
Yes, it's viscosity divided by magnetic diffusivity.
Yeah, so it's either the Roberts number times the Prandtl number, or 1 over the Roberts number times the Prandtl number.
Yes. So
that's also infinite. So yeah.
And so so in this way, it is in the same line of Emmanuel Dormy work.
Yeah, it's very similar in that sense, because Emmanuel, it's even more similar, because I think Emmanuel actually talks about a large magnetic Prandtl number, doesn't he?
Yeah.
But he non-dimensionalizes his equations slightly differently. He non-dimensionalizes his equations with eta or with nu. I can't remember. We use kappa. And so where we would get a Prandtl number, in our inertial terms, we would get a 1 over Prandtl number times the inertia terms. I think Emmanuel gets 1 over PM times inertia terms, just because he's used a different scaling, but it's the same idea. Yeah.
But does he keep the inertia term?
No. Yes, he does.
Okay.
And that's right. He keeps it and he makes it kind of artificially larger. Well,
okay.
he makes the Prandtl number artificially larger to make to push down the inertia term.
Okay.
So he does have it, but it's small, and it's interesting what he finds. I mean, he finds this. He can map out this weak field, the weak branch, like in that sketch of Roberts, and the strong branch. He finds the turning and everything. And he concludes a bit like us in a way that, or we are like him, that getting rid of inertia is what you need. And that's how he does it. We go to the extreme. So I think Emmanuel's magnetic Prandtl number is something like 20 odd. And we make it infinite.
Okay.
But as I say, it's good in a way to make it infinite, because you actually get rid of those fast modes that you don't need. On the other hand, it's harder work because you have to invert the operator. And in a spherical code, I can see that can be a bit painful, which is.
Okay, thanks a lot again.
The question is there in the chat box, so you want me to read, or you can read and.
Maybe can you read it? For some reason, once I share my screen, I can't.
Okay. I will read the question. So your equation corresponds to infinite Prandtl number convection, but convection in Earth outer core is low Prandtl number. Can it affect the balance between the kinetic and magnetic energy? You're getting very small magnetic energy. Can it become comparable if you use low PR values? So low Prandtl number is asking.
Yeah. Okay. So this there's some very good points there. In a way, it goes back to just what just saying to Frank a minute ago. I mean, you're right in that in the Earth, the Prandtl number is not infinite. What we would say, so actually the coefficient in front of the term is not just 1 over Prandtl number. It's got an Ekman number in there as well. And so what we would say is that by making the Prandtl number large, or in our case infinite, you are putting yourself in the correct regime. And so that's what you have to be careful with, because you could just keep decreasing the Ekman number without getting yourself in the right regime. Of course, if you're in the full Earth regime, which is small, this is how we would argue it. The full Earth regime, of course, is incredibly small Ekman number, 10 to the minus 15, and small Prandtl number, but not as small. Okay, so that Ekman number over Prandtl number is small. That's the crucial thing. Ekman number over Prandtl number. And so in a numerical simulation, that's what you want to keep small. And that I think puts you in the right balance. So it's not really, the Prandtl number is small or something. It's Ekman over Prandtl. And so Ekman, even though we've got a small Ekman over Prandtl for us is definitely small. As it is in the Earth. In the Earth, it's the ratio of two small numbers. So in a way, you could think of ours as an expansion in Ekman over Prandtl. And that's the real. So we think by doing that in an extreme way, but by making Ekman over Prandtl small, then we are in the right, quote, right regime dynamically. So that's how we would think of that. Yeah, okay, the point about the magnetic energy. Yes, you're saying it's very small, okay, but it's been scaled with something very large. Okay, let me try and explain this without getting myself into too many knots. If you want your magnetic, suppose you've got the Prandtl number in the problem and you want to make the Lorentz force come in at 0th order, then you have to scale the magnetic field essentially with the Prandtl number. If you scale the magnetic field with the Prandtl number, then it comes in at first order in your momentum equation, even when you let the Prandtl number tend to infinity. So in some sense, the magnetic field is huge because it's been scaled with something which becomes infinite. So these things are very subtle limits in a way. So it's very hard. It's very hard to make estimates of magnetic energy once you get rid of the inertia terms and all the scalings. But you shouldn't just think that the field is small because it's been scaled with something very large, the Prandtl number, in order to come into the equations at this order. So it's a subtle kind of ordering. Yeah, that's. I mean, I could go into it in more detail, but that's.
I got your point.
Okay, so I'll ask you 1 or 2 questions, David, before you close.
Okay.
So one thing is similar to what you commented on the last comment. So magnetic field is small. So J cross B term, unless you scale by like what you just said, it should be pretty small, no? So you said that you are scaled with PM. That's why it is coming out to be significant.
Yeah, otherwise you don't. Otherwise, in this limit, it just doesn't come in. That's right.
Yeah. So UM is also scaled, or UM is not. When UM is scaled, or the magnetic velocity field component.
No, it's not. It's not scaled again. No. I mean, how I think of it is, if you want to think of this through taking the Prandtl number large, then you have to scale your field. If you don't scale your field, then the Prandtl number, then and go to infinite Prandtl number, then the field won't even come in. So you have to scale your field to get it in. Otherwise, there's no dynamics of the field. Yeah.
Okay. So the next point I wanted to make is we did something on Taylor Green, in fact, with Rakesh Yadav, Taylor Green dynamo with low Prandtl number. So high Prandtl number and low Prandtl number. And large Prandtl number, we got supercritical pitchfork. And low Prandtl number was pretty similar to what we showed with going back and coming down. With the Dormy, it was 1-to-1. I mean, there was a really 1-to-1 mapping. And there are two branches, weak branches. So I sent you the reference. So with Taylor Green 2 shows a very similar feature. So, I mean, I don't know. I really, we were arguing why low Prandtl number, low magnetic Prandtl number. So there was no convection. It was just Taylor Green dynamo. So U and B. And just by turning down the magnetic field, turning on the Prandtl number, we were getting supercritical.
Yeah,
now,
I mean, that,
we weren't.
Yeah, I mean, that's very interesting, actually, isn't it? In the sense that in the rotational case, you kind of think, oh, I'm offsetting the, you know, I'm balanced. I've got a balance between Coriolis and Lorentz and things like that. So in a Taylor Green, that's quite interesting as to even what your balance of forces, you know, what are you offsetting against what to get this subcritical dynamo?
Yeah, so what we argued actually, in fact, Rakesh, me, and we talked with Stephen Fove and Dormy as well. We felt that low Prandtl number is more turbulent or more nonlinear, no, because their nonlinear term is more active. Like, in fact, you're doing other way around. But we are only keeping the U field and B field. So more nonlinearity means higher order terms. So remember the term like X. So 1D bifurcation equation, which is X dot equal to X minus X cube plus X5, which is used for subcritical transition. Yeah. So X dot is C1X plus C3X cube gives supercritical, but you put another term X5 that gives you subcritical bifurcation.
Yeah.
Which people only use. So we use that and we argued that, okay, low Prandtl number is more likely to have higher order terms and that will lead to supercritical. But just wanted to make a comment from what.
Yeah, no, I must look at that in your work in more detail, man, because that's a very interesting issue. As to,
so I will send you the paper, and when your comment, I mean, we can also exchange some ideas after.
Yeah, because so, that's because in a way you're doing there, or we're doing in our thermokinematic problem. That's essentially what we're doing, but instead of, I mean, you would have a Taylor Green forcing, and we would have a convective forcing, but it's just a forcing. It's just a forcing because we constrained it to be a forcing. So those are similar in some sense, different forcings, but yeah.
That's right. So your magnetic equation, does it become more nonlinear, or, I mean, it's a magnetic equation which is leading to bifurcations, B equation. And that's where, well, let me send you the paper, then you can think about it. Of course, you've done quite a bit of play around with many terms, of course. So this is all interesting. So I think we don't want to hold you longer. I mean, we had 35 minutes of question answer.
Well, thank you very much for all your questions and everything. It's been great.
I'm glad that you liked it, but your talk induced so many questions. So thank you for a very nice talk. It was quite a broad topic, you know, so we had covered quite a bit. So we thank you on behalf of all the audience. And so we close now. I mean, I guess there's no other question from the audience.
Okay, well, thank you, everyone.
Goodbye, David.
Bye, everyone. Bye-bye.
Thanks a lot.